Exercise 41.10. The exercise is to be solved with the assistance of the TI-Nspire CX CAS version 3.2. Consider the region bounded by the graphs of y equals 2 the square root of quantity x plus 5 minus 3, y equals to 1 minus the square root of quantity x plus 5, and y equals 1 minus 5 times the square root of quantity 7 minus x. Part A. Provide a graph of the region. Part B. Provide a graphic approximation of the area of the region. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. E. If able, obtain an exact value for the area of the region. Part A. Provide a graph of the region. Okay, I would like the first page to be a solution summary, and then all the following pages will be supportive documents to all that. So starting off by adding a notes page here, and I'll title this as exercise 4.10 solution summary. Part A, this will be the graph of the region, and I plan to put that on page 2, so I'll tell the reader just that right here. Something else, since this is the title of the first page and really the title of the document, I would like to have this more bold with even larger font if possible. So come in here, format the text. Let's go to bold, jump up a size on the font, and click escape to get rid of that. And now I would also like to center this a little bit. Okay. On to page 2. Control. Add page. Graphs. Okay, the entry line has opened. We're being prompted. And alright, we have our equations here. Something you might do, it's just good practice, and that's try to anticipate the shape of the graph even before you have the Nspire produce the results for you here. So this first one, y equals square root of quantity x plus 5 minus 3. What to think? Well, right off the bat, you could say that this is going to be a semi-parabola having a horizontal axis of symmetry. That much you know just because you see a y equals 2 square root of linear expression in x, and the minus 3 will translate it down 3 units. You can do an even more in-depth visualization of this if you have studied transformations and you have memorized the graph of the quintessential semiparabola y equals 2 the square root of x. So here we have f1 of x equal to control square root of, enter. Okay, the second one here, push the tab key to reopen the entry line, and we have this y equal to 1 minus the square root of quantity x plus 5. What to expect? Let's try to anticipate. Just recognize this as being a y equals to a square root of a linear expression in x, and therefore it's a semi-parabola with a horizontal axis of symmetry. Okay, so to a lesser or greater extent, do try to visualize ahead of time when you can. Good practice for you. And a part of really knowing your math is when you can just by looking at an equation, you can visualize the graph. Alright, here we are. Go 1 and minus. Enter. And there is yet a third equation here. Alright, let's re-hit the tab key to bring back the entry line with the f3 of x waiting for us. What have we got here? This says y equals to 1 minus 5 square root of 7 minus x. Okay, a quick visualization would be to say, a semiparabola, horizontal axis of symmetry. More in depth by knowing transformations. Okay, let's proceed. The formulation. 1 minus. And enter. Okay. Well, alright. Knowing these were all semi-parabolas, we know that we have in sight right now the only possible enclosed region. There is nothing else to worry about. That's the advantage of knowing the shapes of your graphs before you graph them, just by looking at the formulation. And let's see then, since that's the case, let's make this enclosed region large to fit into the screen. And to do that, I think I will first use a zoom box. So menu, window zoom, zoom box. Alright, first corner. I want this to fill the coordinate system and still have room to put labels. So I also leave a little room for labeling. I think about there. And the second corner. Think about there. Okay, I'll escape to put that tool away. Let's see if this is going to be the right amount of room. I can move this up here and over a bit to prepare for the labeling of the intersection coordinates. This label can go here. And let me grab this F3 of X label. If it went there, okay, everything is there. Now let's see. These axes are scaled, I think, too densely and with clumsy looking numbers there. So I think I'll fix that up. So let's go back to the menu and go to the window zoom, the window settings. Okay, let's keep things simple here, like a -3. Tab, maximum of 8, tab, scaling, let's see, right now the x-axis is 11 units long, 1 unit per tick mark, I think will be fine. Okay, the y-axis, I'll say a -4, and a 2, perhaps. It's 6 units long right now, so scaling that at 1 apiece would probably look fine. Click OK. Okay, I think it looks a lot cleaner. Great. Now, let's see. We would want to, of course, shade and label the enclosed region very clearly. And one nice way to do that would be to use a polygon and shade the polygon. Actually, what I think I will even do ahead of that is get the points of intersection here. Okay, so let's see. To do that, you could go with the menu and the geometry and points and lines and intersection points. Okay, well, the way this works is you select the two graphs and all their points of intersection will appear. So let's say F1 and F2, for instance. Okay, that right there, -1, 1, has appeared as the intersection point. By the way, before I go further, there are almost certainly going to be some complicated type intersection coordinates here, and I don't want to see a huge number of decimal points, decimal places appearing. So what I'm going to do now is get this graph with its settings in order, and I think since I would like to see 2 decimal places for any coordinate, and I think the area looks to be a rather small number, not requiring too many decimal places, I'm going to go with a float 2 on this graphing setting, and I think that'll make things look rather nice. Okay, that's done. Alright, our tool of intersection points is still open, so let's now pick graph 1 and graph 3. Okay, got that point there, and let's see, one more combination, graph 2 and graph 3. Okay, got those points there. I'll put away the tool, and now let me put these coordinates in better looking positions, out of the way and not inside the region. There and there. Let me move this over, bring this down a little bit. Okay, that looks pretty good there, I believe. Now onto the shading of the region. For this, I approximate it with a polygon and then shade the polygon and then remove most of the polygon. So here's how this goes then. Menu, geometry, shapes, polygon. Okay, let's start off with there and okay, push escape, put the tool away, and now I want to shade this polygon, so select it, context menu, and color, fill color, I'll choose yellow. Okay. Now before I go further, this polygon that I'm using to shade is also very valuable to me as an approximation device for part B of this question. So I'm going to actually create a copy of this page because it's like I've hit a fork in the road. I want one graph to proceed to be a graph of the region. I want another graph to go on to become a graphic approximation. So what I'll do is I'll go Control, Show Document Pages. I will just copy and paste here. Now back to page 2 to continue with what's going to become our graph of the region. Now, the black outer lines of this polygon are distracting, and so are most of the vertices of the polygon, so I'll get rid of all of that. Okay, first I need to select the polygon, and then go back to color, and this time it's the line color. I want to make that yellow. Okay, and then some of these vertices, not the intersection points, but the other vertices are distracting, so it's a matter of going point and hide it. Okay, lastly, the person looking at this graph, I want them to have no doubt about what I've done here, so I'm going to label the bounded region with some text. Context menu, text. Okay, I think that is now a pretty good looking graph. All of the individual graphs are there, labeled with their equations. The bounded region itself is clearly shaded and labeled. All of the intersection points have been provided with their coordinates. And of course, the coordinate system has labeled and scaled axes. All the elements of a good graph are there. That's set. Part B, provide a graphic approximation of the area of the region. Let's go to the graphic approximation of the area, waiting for us on page 3 here for completion. Okay, we have this nice polygon. This is what we will use as an approximation device. Let's select it, context menu, and go to a measurement of the area. Okay, got this 12 square units here. Let's just put in a little text so to clarify just what that means to someone looking at this graph here. That looks pretty nice there. I want to record this result on our page 1 though as well. That's our summary page. So 12 square units. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. For a calculus calculation of the area of a region, a fundamental strategy is to slice up the region and then sum the areas of the slices with an integral. Surely the most popular slice is the thin vertical rectangle. Let's try slicing up our region with thin vertical rectangles right now. Okay, let's think about informally formulating the area of each of these rectangles. It's simplest when all the rectangles have the same area formulation, because then we can sum their areas with just one integral. How about here? First, we see that the tops of the rectangles are all defined by the blue F1 graph. That's a good start. Next, we examine the bottoms of the rectangles. Okay, there is a change at the far right of the region. The bottoms of the rectangles changed from being defined by the red F2 graph to the black F3 graph. So now we have two fundamentally different types of rectangles, and consequently we'll need two integrals to sum up their areas. So let's informally formulate the areas of these rectangles. Like all rectangles, the areas will be length by width. For the thin vertical rectangles in the vast left portion of this region, the length of any one of those rectangles will be upper y minus lower y, which translates to f1 of x minus f2 of x, width dx. For the thin vertical rectangles in the smaller right-hand portion of this region, their length becomes upper y minus lower y, which translates to f1 of x minus f3 of x. Their width, in each case, is also dx. Taking into account our visualization here, we've got a strategy. Let's tell the person reading our solution what we have in mind here. First, let's go and store those variables of integration into A1A, B1A, and C1A. For that, let's return to our graph of the region. Starting here, we'll go ahead and take this and store it into variable A1A. I chose that just because the leftmost bound of integration in calculus is traditionally chosen as A. I go and add a 1 because I don't want to use single letters when using the Nspire for variable names. And then the suffix A is to indicate this, well, maybe an approximate limit of integration, not necessarily an exact. And now let's go to the second one. Okay, here 6.5 is less than 7, so let's grab this and go to store. Okay, B1A, and enter. This one here is next, and store C1A, and enter. Remember, this 6.5 or this 7.0, these are just the displayed digits. The Nspire always has something like 14 digits that it carries on internally. It doesn't show them. By storing it into variables, we access that full 14 decimal place precision. Okay, now let's go ahead and return to our notes page since we have now stored the variables as we said we were going to. Area equals to, alright, time to go to the menu, calculations, calculus, integral. Alright, we're going left-hand limit is A1A, tab, B1A, tab. Alright, the height of these rectangles as we look back at our diagram. Now make another forward arrow, and now plus. Okay, that second collection of thin vertical rectangles. To sum those up, it's another integral. Okay, this one goes from B1A, tab, C1A. Alright, now from our diagram, the heights of these rectangles was the f1 of x minus f3 of x. Okay, and enter. Alright, got this number here. Let me tack on the square units. And let me kind of fix up this math box a little bit. I like that little triangle to be an approximately equals to. So, context menu, math box attributes, And that insert symbol, make that an about equals 2. Click OK. There we are. Now, another little item here. The question, formulation, it says 5 significant digits. We're showing 6. Too many. Okay. There's two ways we could fix that. You can actually, at this point, go to a math box settings itself, but I want to fix this up just for the entire document. So I'm going to go here to document and settings and document settings, and I'm going to have this be float 5 so that I'm always only seeing 5 significant digits, be I in the math box or a calculator application. Okay, there it goes. Cut it back to 5 significant digits. Now we are in line with the instructions. Part D. Assess the correctness of parts B and C by examining for a consistency between the two results. Alright, let's record what we said about the graphic approximation. That was 12 square units. I'm just going to record the numbers here since that's the key of looking for the consistency here. And the calculus calculation is still in sight there. Alright, as we compare those two numbers, this is some really good news. 12 versus 12.223. Okay, well, looking at the larger number there for the basis as is traditional, 10% would be 1.2 difference. These are only differing by 0.22, so even if we say 5%, that's a 0.6, so we can claim these are within 5% with not at all exaggerating. So therefore, these are consistent. Therefore, we believe the solutions to parts B and C are likely correct. Okay, great. Part E. If able, obtain an exact value for the area of the region. For an exact calculation, the first thing we have to attempt is getting exact limits of integration. Alright, well, let's see if we are even able to do this. And let's take all of this calculation off of the summary page here and put it on an attaching page. We're going to need to use a calculator application, so I think it's a good time to open up a page 4 here. So let's go to page 3 and then control add page. Now that we have this calculator application open, let's return to page 2 and visually see which graph intersections are needed to exactly solve these limits of integration in ascending order. Okay, looks like the leftmost point of intersection is a result of the intersection of F1 and F2, and we seek the x-coordinate of this intersection. Solve. Okay, for the sake of a uniform appearance to this calculation, I will come up here and take that -1. So over here, shift left arrow to select that number, enter to paste it on the next new line, and control store to. Alright, this is exact, so I'll call this variable A1. Enter. Alright, the next calculation would be to solve F2 of x equals F3 of x. So I can just edit this same calculation from the earlier line. Okay, we have that. And selecting this, pasting it here. Now we can control store to. We'll call this B1. Okay, this is an exact second limit of integration. And now that last one, that's the F3 equal to F1 of x, solving for x. So we can go up here, select that, paste it here, and then just edit it to say F1. Okay, that somewhat messy looking number. Select it, enter to paste it here. We'll store that into C1. Okay, well, we successfully got exact limits of integration. That's the first big obstacle in this calculation. Okay, and let's point that out to the person reading our solution here. And let's also point out that the limits of integration, the exact limits of integration in ascending order, have been stored in variables A1, B1, and C1. We want to point this out to the person reading the solution so that they will understand the subsequent sum of integrals we're about to use in this case. Alright, I think I'll try to save a little time by coming up here. I have this. I want to go here. Shift, go to the right with an arrow until I get the two definite integrals. I'll go Control C to copy them, and I'm going to go down to the end of my document here, and right here Control V, paste them. Now some editing is in order here, so okay, for instance, just backspace to make that a C1. Down here, delete, make that a B1. Over to the other one. Okay, A1A replaced with its exact analog A1, and up here B1A replaced with its exact analog B1. Okay, let's see what happens after we hit enter. Oh, okay, got an exact result. Pretty complicated looking, but it's exact. Okay, let's touch this up a little bit. Come here and change that little arrow to an equals to. This is exact. There we are, and add on square units. Okay, now for the sake of peace of mind, we would probably want to double check this exact result here. Make sure it is really the same as we're seeing in part C, at least approximately the same to the 5 significant digits we've recorded. So let me take this number. I'm going to go shift and arrow over to select this number here, and Control C, and down here I'm going to say this. Alright, now I'm going to go to a actions, approximate. Okay, good. That's consistent with the result of part C. Just going to change this to say about equals to. Okay. Okay, great. We got everything in order. Pretty solid solution. Got the consistency of the graphic and the calculus solutions, and we were able to even obtain this area exactly as well. Great.